Okay. All right, guys. Welcome back to another week of interactive session of the course Fundamentals of Conduction and Radiation. And today's class, as you know, is a extra class taken in the fact that we have missed the class in the last week, and this is basically a readjust class to the missed class in the last week. And yeah, welcome back. So we met yesterday, and then again we are meeting today. So thank you for joining once again today, although it being a Sunday. Yeah. So what we will do today is what we will do is we'll again so you know the drill by now. So we'll begin by quickly having a revise of what we learned in the last class, that is yesterday, and then we will proceed with the discussions on today's. Yeah, so we'll proceed with the discussion on today's class. So quickly, let's do a quick recap of what we learned in the last class. And so what we saw is basically something which is known as 2D heat transfer. And just a second. And so what we saw is that so mostly until the last class, we dealt with something which is known as a one-dimensional heat transfer, where the direction of heat transfer or the heat flux was basically in one dimension. So now we have added a bit more complexity to our analysis, where we looked into the case where we can have a temperature distribution which is two-dimensional. And we saw that the basic governing equations in the case where there is no heat generation and it's a steady state problem, the basic governing equation just boils down to the Laplace equation, as you can see. And we saw the characteristic of this Laplace equation, and then like we saw certain strategies through which we can basically solve this Laplace equation. And one of such techniques is the method of variable separation that we saw, where we were to solve the temperature distribution of a rectangular plate. Now it's a 2D problem that we are solving, whose three faces were at constant temperature. And here it was said that the temperature is basically 0 degrees Celsius. And the upper plate is having a variable temperature, which is basically some constant times x. So we could solve this problem. If you remember, we could solve this problem using the method of separation of variable, typically because at least in one direction, that is, let's say at least in the x direction, we have something which is known as a homogeneous boundary condition. For instance, at x equal to 0, the surface was maintained at t equal to 0. And let's say at x equal to a, the surface was also maintained at t equal to 0. So because of that, we could use the method of variable separation. I'll quickly ask you a very simple question. Let's say I have this simple problem only. I have this problem only. But now let's say I tell you that instead of this T being equal to 0, I say let's say this is a non-zero temperature that we have. Okay, let's say this T is 5 degrees Celsius, for instance. And this T is also 5 degrees Celsius, and this T is also 5 degrees Celsius. So my question is, if this is the scenario, and yeah, the upper surface is still a variable temperature having the value of T equal to some A times X. Now, if this is the scenario, can you tell me, can I still apply the method of variable separation? And if yes, how can we, what do we need to do in order to apply the method of variable separation? Let's say I say this is some not T, basically let's say this is some, let's say T naught. Can you give it a try? That if I now have this scenario where now the three faces, instead of it being at 0 degrees Celsius, now they're at 5 degrees Celsius, and the upper face is still at the temperature T equal to AX. My question is, can I still apply the method of variable separation in this scenario? Okay. Can Just 1 second, guys. Just think about this. Just 1 second. All right. So the answer is okay. I didn't see any answer here. Okay. So the answer is yes. We can still apply the method of variable separation, But for that, we need to do a very simple step. What we need to do is we now need to take a temperature. We now need to, you introduce a transform variable of the temperature, let's say theta, which is basically the temperature T at x equal to y minus T naught. Okay. So what we need to do is we just need to introduce this transform temperature. Now, instead of like evaluating this T of xy, we'll basically evaluate this theta. So if we do that, and if we write the boundary conditions of theta in terms of instead of t, what we will see that if we use this transformation, we will see that this theta is basically 0 here, this theta is basically 0 here, and theta is basically 0 here. Solely because I have taken theta as this temperature T of xy minus T naught, which means if I evaluate this theta at this phase, then theta becomes T equal to T naught minus T naught, and then it becomes 0. And similarly, the same analogy can be drawn from this and bring this phase. So if I just very cunningly, if I just use this transformation, okay, then even if we don't have a 0 degrees Celsius temperature on these phases, we can still make our boundary conditions homogeneous just by using this simple transformation. Okay, so this is the idea. This is the idea. Even if let's say you may encounter in one of your problems, then you may not have the temperature to be equal to 0 degrees Celsius on the faces, and then still you can apply the method of separation of variable just by transforming now to a different variable theta, which is basically the temperature minus the temperature on the three faces. Okay, that's a simple transformation that you need to do, and then the rest is as similar as we did yesterday. Okay, so we'll not go into the details of this much because we have seen this yesterday. So basically it was a long procedure, and thereafter we have used something which is known as the orthogonality and the boundary condition by separating the variables and all those things. And after doing that, we finally found out the temperature profile would look basically something like this. Now, you may question that why are you doing such a long algebra? Because like in practical sense, if you give me a problem, it will take at least for me a half an hour to, even if, so if you are an expert, at least you will take around 15 or 10 minutes to basically solve this problem. The beauty of, using this method of separation of variable is that this gives us an exact solution. Okay. All other method, let's say the finite difference method, you can use it. You will see this later on that you can also solve this problem using something which is known as the finite difference method, which is used to discretize the governing equation into a algebraic equation. Okay, but nevertheless, all other methods that we will see, or at least you will see in this course, these are approximate method. But this separation of variable, this is not an approximate method because we are not assuming any assumptions, or we are not, it's like we are not playing around with the order of the governing equation and so on and so forth. We are just solving the 2D problem verbatim, and just by using something which is known as the eigenvalue expansion or an eigenvalue problem, we have come out with the expression of temperature. And this expression of temperature, this is not approximate. This is the exact expression that basically the problem seek for. Okay, so a natural question arises. I mean, it should be so. You should ask that okay, now I have an exact solution for temperature, but there is a summation sign here, right? So this is summation 1 to infinity, right? So the natural question arises that how long are you going to take this summation? In fact, if I am asked, so if I am just asking you that just evaluate the temperature, then how many values of n are we going to calculate? Let's say, are you going to calculate from n to 5, 1 to 5, or let's say from n equal to 1 to 10, or are you going to calculate from n equal to 1 to 100? Okay, so this is the natural question that it should arise in your mind, that yes, there is this summation sign, but in reality, how much term in this expression am I going to retain in order to like get the accurate solution of this expression? The answer is, the more number of term you retain in this expression, the more your accuracy will be. Okay, but it's not that you will discard the n equal to 1 term and you will take the n equal to 10 term. It's not like the other way around. You cannot discard. So these specific values of n, okay, they are known as modes. And in these kind of eigenvalue expansion, the lower modes are very powerful than the higher modes, which means if you discard, let's say you are writing this summation by discarding the term n equal to 1 and 2, and you are just writing this summation from n equal to 3 to n, then your answer would be haywire. It will not be accurate. Okay, so the takeaway is that you cannot discard the lower order modes, or the lower order modes in your solution are the most powerful modes. For instance, this n equal to 1 mode, okay, is the most powerful mode of this solution, and your solution will just revolve around this n equal to 1 mode. So you cannot discard the lower order modes in your analysis. However, you can discard the 10th mode. You can just take your terms from n equal to 1, 2, 3 up to 5, and this would be a good level of accuracy in your problem. But as I said, you cannot discard the lower order modes. Okay. So remember, in any eigenvalue problem, this is just a simple eigenvalue problem that we solve. But like when you go into your higher classes, or like when you will go basically into more depths of subjects involving partial differential equation and separation of variable, you will see that lower order modes are most powerful modes. Most powerful in the sense that these lower order modes decay less slowly than the higher order modes. Okay. And that's why you cannot discard the lower order modes in a eigenvalue problem expansion, but you can discard the higher order modes, and you can continue taking the modes so long as you are like, so it's a trade-off. Like, so basically you need to solve this in a computer, right? If you want to like put this in a computer, your computer will basically ask how many modes of n are you going to take, because you cannot go till infinity, right? So based on the preciseness and the accuracy and the power of your machine, okay, you can, so there is a trade-off between your accuracy and the number of modes that you are taking. I repeat, you cannot discard the lower order modes because the lower order modes decay less slowly than the higher order modes, and your solution is typically dependent on the lower order mode, that is your modes of n equal to 1, 2, 3, and so on and so forth. Okay. All right. So this is something that I want to convey. I forgot to tell in the last class. Uh, and then we learned something which is known as the shape factor analysis. This was relatively simple because this was a more practical sense of like solving 2D problems, where basically the rate of heat transfer is just governed by your shape factor multiplied by the thermal conductivity into the temperature difference. Where I said that depending on the geometry that you are solving for, okay, you have the specific expression for the shape factor. For instance, in this case, I have a sphere that is in a semi-infinite medium, and then the expression of shape factor was basically something like this. Let's say if I have a cylinder, that is the other problem that we solve. This was basically your assignment problem, and then the expression of shape factor was basically something like this. Okay, so these things is something that we saw, and then yeah, this is a similar problem. We will not go into this problem because this is exactly associated with the shape factor only. So let's not go into this problem. But anyways, this is up to where we stopped in the last class, that is yesterday. I'll wait here for a couple of minutes. In the meantime, if you have any doubts associated with the contents of the last class or the contents of the week's lectures, or anything related to your assignment, you can just feel free to, I mean, ask, or else we'll proceed with something which is again a very interesting topic. It is known as transient conduction, and yes, we'll proceed with that with today's discussion. Okay, I'll stop here for a couple of minutes. If you have any doubts, you can just ask. All right, guys. If no doubts, then we will proceed with something which is known as transient heat conduction. And by the name transient, it suggests us that now we are adding one more complexity into our problem. Now we will look into something which is known as the unsteady problem, because till yesterday we took into the assumption that all the solutions and all the methods that we are dealing with, be it a 1D or be it a 2D, the very assumptions that the very assumption that we consider is that our problem is a steady state problem. But now we'll relax this assumption, and then we'll move into something which is known as an unsteady problem, or in the language of heat transfer, it is known as transient heat conduction. Okay, and there are many examples in transient heat conduction, but one of the most important example and one of the most simplest case of a transient heat conduction, and one of the most important case for your, like, for this course and for your exams, is something which is known as a lump capacitance. So this is something known as the lump capacitance model. Okay, this is the most simplest example of transient heat transfer, and this model is known as the lumped capacitance model, and we will see, although we'll not go in much the theory of this because we have already seen that in your lecture classes, but we will kind of understand based on the questions that you will need to solve in your assignment, the theory behind this lumped capacitance model with some numerical aspects and also some nuances of this lump model. And if we have time, today we will also see something which is known as a semi-infinite solid, and if not, like we will see this semi-infinite solid in the next class. Okay, so the very name suggests that your model is the lump capacitance model, is basically described by the fact that your temperature, let's say of a body, if you are using the lump capacitance model, your temperature is spatially uniform, which means that let's say you have a body. Okay, this means that your temperature inside this body, okay, is not a function of its position. That means your T is not a function of X. This is not, this is not possible in this lump capacitance model. Okay, that means that we have simplified our temperature field now, saying that throughout the body, okay, my temperature field is not going to be varying with time. So can you tell me under what circumstances is this, like physically is this possible? That, let's say, it's very simple. Let's say I have a body at some temperature, initial temperature TF. Okay, this is let's say a very hot temperature, let's say 150 degrees Celsius. Okay, suddenly what I do is I drop this body into a fluid, let's say water, at 0 degrees Celsius. Now this process is known as quenching in heat treatment, or in material science. Now in this quenching process, you can assume that, so naturally what will happen if you have a body at 150 degrees Celsius being dropped into a fluid at 0 degrees Celsius, this body at, let's say, at some time t equal to 0 plus, this body will basically cool down, its temperature will come down. Having said that, we will still assume that even though its temperature will come down, its temperature will just be a function of time, and it will not be, so it will just be a function of time. Okay, and it will not be a function of x and time, that is, it will not be a function of its position inside the body. So my question is, under what circumstances is this, so this model is known as the lump capacitance model. As I was saying, we will see why it is called the lump capacitance model, but anyways, can you tell me under what circumstances the prescribed, like, paradigm that I said is valid, or the lump capacitance model is valid? Okay, this is the first question you need to understand before, like, you go into the details of this lump capacitance model. I'll give you some time, like, can you tell me? Yes, any answers? Okay, so I'll give you a hint. uh, so I'll give you a hint. So when I say that my temperature is not varying spatially inside this body, means that when, let's say, this body was at temperature Ti, it will now go to some temperature T final in some given time T. This means that I have neglected the conduction resistances inside this body. Okay, or in a better sense, I could say that the dominant mode of heat transfer that is responsible for this body, okay, that is responsible for lowering the temperature of this body from some temperature Tf to some temperature Ti, is basically the convection heat transfer that takes place between the interface of the body and the fluid. Okay, and we will see that under these circumstances, when the conduction resistances inside the body is less dominant, or it is very negligible to the convection resistances that take place between this body and the fluid interface, under this scenario, okay, you can assume that your temperature is not spatially varying with s, and this we will prove it mathematically. Okay, and in the language of heat transfer, this physical picture is given by a quantity which is known as the bio number. I think you have learned this term. This is known as the bio number. And for your lump capacitance model to be valid, your bio number should be very much less than 1. Okay? And physically, as I said, your bio number is basically the resistance. So it's basically the ratio of the conduction resistances inside the body to the convection resistance taking place between this body and the fluid. Okay, and if, as I said, your bio number is less than 1, this means that your conduction resistance is less than the convection resistance between the interfaces of the body and the fluid. And in the case where your bio number is less than 1, you can rest assured and apply the lump capacitance model, and we will see this, like, and we'll try to prove this mathematically. Okay, so if you remember, the governing equation for this lump capacitance model will not prove it, because this was already done in the theory classes. I mean, in this week's class. So we'll not prove the governing equation, but we saw that the governing equation which governed the lump capacitance model is basically something like this. So it was theta by theta I. Okay, I think I'll learn. Okay, maybe I'll write it here because I've already created um, this. So this was the same problem that I said. So there's a body, okay, which was basically, so it was initially at some temperature Ti, and Ti is much greater than T infinity, let's say. For instance, a metallic ball, which a metallic ball at initial temperature 150 degrees Celsius is now suddenly dropped into an ice bath of, let's say, the temperature to be around 0 degrees Celsius. This is the scenario where exactly the lump capacitance model is basically applied. Okay, and in that context, if you want me to write the governing equation is basically something like this. So it was theta by theta I is basically equal to, and this theta is nothing but t minus t infinity by ti minus t infinity. So theta is basically this. So theta I basically becomes ti minus t infinity, and this is equal to exponent of, so it's a number, so it's called exponent of minus t by tc, where this tc, this tc has got a value of rho times the volume of the body times the heat capacity divided by heat transfer coefficient times as. So this tc has got a special name. This is known as time constant. Okay, and this was precisely the governing equation which governs how your temperature will basically vary with time. Okay, in your lump capacitance model. And as I said, your temperature, which may be theta by theta I, or it is basically this temperature. These two are basically the same. Okay, you can see that your temperature is now just a function of time. It is not a function of space. Okay, and that's why this model is known as the lump capacitance model. Okay, simply because you are assuming that the conduction resistances inside the body is less than the convection resistances, or it's very negligible compared to the convection resistances taking place between the body and the surrounding fluid. Okay, now if you ask me how do I get this expression, the detailed derivation, it is being showed in the week's lecture, but the broad idea is that just consider this as a control volume, apply the energy principle, which is basically minus E dot out is equal to the rate at which the energy is being changed. So it's the rate at which the energy is being changing inside the control volume. So I'll write it as, let's say, E dot storage. And if you just, so E dot out is basically H times minus H times A times T minus T infinity. And this E dot storage is basically minus, it is plus rho times the volume times the specific heat capacity times dt by small t. Basically, it's the rate of change of how, it's basically the rate of change of the stored energy. Okay. And if you just solve this governing equation, okay, you will simply end up getting this solution, getting this simplified. So basically you need to integrate this equation, and then you can see it's very straightforward. You will just end up getting this nice little expression of your lump capacitance model, which dictates how your temperature will now be a function of time. All right. So as I said, your expression is basically this. You just need to apply this expression where this Tc is known as the time constant. This time constant is a function of many properties. It's a function of the density of the material. It's a function of its volume. It's a function of the heat capacity divided by H by AC. Now, can you tell me what is this ratio of V by AS called? Can you tell me? What is the ratio of a particular body? What is the ratio of its volume to its surface area? Yes, exactly. It's known as the characteristic length. So this ratio is known as LC, which is basically the characteristic length of the object. For instance, can you tell me if I have a cube of, let's say, side A, can you tell me what is the value of LC? Quickly. That's easy, right? Can you tell me? That's also a part of your assignment. Can you tell me if I have a cube of, let's say, side A, what is its characteristic length? That's simple, right? Because the volume is basically what? It's A cube. And what is the surface area of a cube? Yes, what's the surface area of a cube? That's simple, right? So the surface area of a cube is just 6a square, right? Because you know that the surface area of a cuboid is basically, it's basically what? So it's basically 2 times the length breadth plus breadth height plus the height length. But for this cube, these things are just equal. So you can just write it as 3 times of a square, and 3 into 2 basically becomes equal to 6. So it's 6a square. Okay. So the characteristic length, of a cube is basically equal to a by 6. Okay. For instance, if you have a sphere, if let's say you have a sphere of radius r, then your characteristic length. So can you tell me what is the characteristic length of a sphere of radius r? Again, the characteristic length is volume divided by the surface area. Yes, exactly. It's r by 3. That's simple, right? Okay. So, nevertheless, the expression, I write it once again, that you will basically use is basically this theta by theta I, which is nothing but t minus of t infinity by ti minus t infinity is equal to exponent of minus t by tc, where this tc is the time constant, and it can now be written in terms of the characteristic length as rho LCC divided by H. Okay. This is all about the lump capacitance model that you first need to know. Okay. So this is all that you need to know while solving problems related to the lump capacitance model. But you must be very clear so as to when the lump capacitance model is valid, and that we will show very shortly, so as to when this lump capacitance model is valid. But like at least this is something that you need to use. So once you are confident that your so I said repeatedly that your bio number is basically less than a certain value. That certain value we will see. But once you figure out that your bio number is basically less than certain value, then you can straightforward use this expression of lump capacitance analysis to basically find out anything that you are asked for. For instance, they might ask you that for a given time, they might ask you to determine this temperature of the object, given that you know the ambient temperature and the initial temperature of the object, or the other way around. They might say that, let's say, your temperature of the object reaches to some definite temperature, and then you need to figure out what will be the time. Because as you can see, your time constant is a known quantity. Okay, because it's kind of, so it depends on what? It depends on the parameters of the object. For instance, the density, the length, the characteristic length, the heat capacity, and the heat transfer coefficient. Okay, so in a way, this time constant is known to you. Either you may be asked to find out this T, or you may be asked to find out this capital T. Small t is the time, capital T is the temperature. When the other way around is given, okay? You might be asked to calculate this T given that you know the final temperature, or the other way around, okay? Now, what we will do is, we will see the most important thing, that is the validity of the lump capacitance model. Because I repeatedly say that under certain assumptions only you can use the lump capacitance model. The more general way of speaking this assumption is that the conduction resistances inside the body is negligible with respect to the convection resistances taking place in the interface. Okay, but that's a more qualitative way of saying, right? You must, so when you will be solving a particular problem, you must have a physical, or it's, so what you say, you must have a demarcation, right? That okay, if my bio number is, let's say, less than a certain quantity, then only I can apply the lump capacitance model. Okay, so for that we will see that this restriction, as I have said repeatedly, comes on the bio number. Okay, and this we will basically see now. So for instance, uh, if I now have an object, okay, let's say what I say is the the axial temperature, or let's say at the axis of the object. So let's say this basically becomes the axis of the object passing through the object. and we say this is the center. So I say that the central temperature, let's say this T, this let's say TS1. Okay. And I assume that now there is also conduction taking place inside this object, which means that the surface temperature would now be different from the axial temperature. And let's say this is some TS2. Okay. And then the ambient temperature is T infinity. All right. And having a heat transfer coefficient H. Okay. Then the same scenario, this object was initially at some temperature, it is being dropped to a fluid, let's say at a lower temperature, then there would be heat transfer taking place from this object now to this fluid. And under, let's say, steady state scenario, okay, although this is a transient model, but this validity of this lump capacitance model can be understood if we look into the steady state scenario of this case, because eventually a transient problem always go into a steady state problem, right, after an initial transients. So this I mean, the what to say, the validity of this lump capacitance model is better understood if I now basically compare the fluxes of this body, that is the conduction flux that is coming out of this body, and the convection flux that goes out of this body at steady state. So what I can write is, uh, let's say at steady state. So I hope you are clear with me. If you have any doubt, just feel free to stop me at any point of time and let me know where you have the doubt. So at steady state, what I can write is the conduction resistance or let's say I don't write it resistance. I can say that the Q dot conduction, that is the rate of heat transfer taking place by conduction from this axis of the body to its surface, is equal to the rate of heat transfer taking place by convection. And now, can you tell me what will be this Q dot conduction given that I have this body? Okay, I do not have any heat generation taking place inside the body. My properties are all constant. Can you tell me what is Q dot conduction in terms of this TS1 and TS2? That's simple, right? That we have done multiple times in this course. Can you tell me? And of course, I say that the characteristic length, I say that the characteristic length of this body is LC, and thus, no, this is not the characteristic length. So this is different. So I would say that the length scale associated with this conduction is, let's say L. The body have a thermal conductivity K, and your area is A. So based on this, can you tell me what is Q dot conduction? Of course, at steady state, because we are trying to understand this at steady state in order to like put a limitation on the lump capacitance model. Okay. Yes, can you tell me? That's simple, right? Because your Q dot conduction would be the temperature difference, that is TS1 minus TS2 divided by the resistance. And your resistance is what? Your resistance is just L by Ka. That we can do, right? Because like we do not have a heat generation taking place, and I'm assuming that the body is basically so and of course I'm assuming that inside the body, inside this body, the heat transfer is one dimensional. Okay, that is, it is being transferring heat only outward from its center towards its surface. Okay, and in that case I can write this as TS1 minus TS2 divided by L by Ka. And the heat transfer due to convection, can you tell me what this would be? This is easy, right? So So this is basically equal to your heat transfer coefficient times your, yeah, it is H, yes, exactly. So it is HA times TS2 minus T infinity. Okay. And remember this, we are doing it at steady state. Okay. So what I will now do is I will just take this ratio. I'll just bring this term to the uh, denominator. Then it becomes TS1 minus TS2 by Ts2 minus T infinity, and this become equal to, what does it become? It becomes equal to L. So I can rewrite this as L by Ka by 1 by Ha. Correct me if I am wrong, but I can write this term as this. So this 1 by Ha, this Ha, I can write it as divided by 1 by Ha, and this basically goes there. So this is basically exactly equal to whatever we have wrote here. Okay. All right. Now, can you tell me what is this? Can you tell me what is this? Yes, this is conduction resistance. Exactly. So this is basically your RTH of conduction. And what is this? This is convection resistance. Exactly. So this is basically your RTH of convection, which means we have simplified this as TS1 minus TS2, okay, by TS2 minus T infinity, and this is basically equal to, so if I just cancel some of the term, I can just cancel this A, and this basically turns out as H times L by K, and this is equal to your RTH of conduction by RTH of convection. And what is this ratio known as? I already told you. What is this ratio, or what is this ratio known as? Can you tell me? What is the ratio of the conduction resistance of the body to the convection resistance of the body? Yes, exactly. This is the bio number. And this ratio is basically known as the bio number. So when I repeatedly said, okay, that for a lump capacitance model, I assume that the resistances, the conduction resistance within the body is very less. This equally means, okay, this equally means that this term is very much less than this term. This also equally means that your bio number is very much less than 1. Equivalently, this also means that your this term, which is the difference between TS1 minus TS2, is very much less than TS2 minus T infinity. Okay, so what I was trying to say is, for your bio number, this is in a short form, it is denoted as BI, which is basically the bio number. So for bio number to be very much less than 1, okay, I can simply write that my TS1 minus TS2 is very much less than TS2 minus T infinity. Okay, which means, so this physically means that my temperature difference between these 2 points is so negligible than the temperature difference between this point and T infinity. And in that scenario, this is only possible when your bio number is less than 1, that your temperature differences within the body is very negligible. And in that case, you can assume that since your temperature difference within the body is negligible, you can assume that your body is spatially, so your temperature within the body is not spatially varying. This, since we have established that the bio number is less than 1, this means that throughout any points inside the body, your temperatures are just the same, because since bio number is less than 1, the difference between the temperature on the surface and on the axis is very less, and you can assume that your temperature inside the body does not vary with x, and in that context only you can apply the lump capacitance model. Okay, is it clear or not? Like, when is the lump capacitance model valid, uh, and the physical meaning of the bio number, and the physical meaning so as to why we say that the conduction resistances inside the body is negligible. Is it clear, or like you want another explanation? Can you just give it with an yes or a no? Okay, all right. Thank you very much. Thank you, Sandy. All right. So, okay. So this means now you have understood when is the lump capacitance model valid, and when I say that the conduction resistance within the body is negligible, or in the other way around, uh, the temperature like distribution is just a function of time, or in the other way around, like your temperature is not varying spatially. All this signifies and just directs to the fact that the bio number is basically less than very much less than 1. Now, if I say it's very much less than 1, now how much is this less than 1? That's the second question that we have, right? So in all practical scenarios, for, for the lump capacitance model to be equal to valid, you can simply check that if your bio number is less than 0.1, your lump capacitance, the accuracy of the lump capacitance model, so it reaches around, let's say, it reaches more than 90%. Okay, so that's why if your bio number is less than 0.1, the lump capacitance the lump capacitance framework is valid. Okay. And now one more thing, and before that, like, we'll stop here for some time. So one more thing is that here I said that this is L and not LC, but if you consider this area to be surface area, then this L can automatically be replaced if you consider this area as a surface area. And in this case, the entire heat is being dissipated through the surface area. So the heat transfer area essentially becomes your surface area. And then in that case, you can write this as LC, and hence you can write your bio number as HLC by K. But remember, if you write LC, then this area has to be your surface area, or the entire area of the body, of the lump body, basically is responsible for dissipating the heat to the surrounding. Okay, then only you can write this as LC, and then you can write your bio number. You can write your bio number as something which is known as HLC by K. Okay. So I hope this is clear. The definition of bio number, the physical significance of bio number in terms of the resistance and in terms of the temperature difference taking place inside the body to the temperature difference taking place from the surface of the body to the ambient. Okay. I hope this is clear. We'll wait here for some time, and then, like, we'll do one more thing before proceeding into the numericals. Uh, but before this, we'll wait for some more time, and then so before, like, stopping for some more time, I'll just end this discussion by writing one more thing. So what we did is we wrote this expression for the lump capacitance model as theta by theta I to be equal to exponent of something like minus. So what was it? It was minus T by Tc. So it is basically something like HT by rho C LC. Okay, so if you just simplify the expression of T by Tc, you will simply get this expression. Okay, now what I will do is I'll do a trick here. So I can just write this expression as exponent of minus. What I will do is I'll first multiply this and divide by LC. So I'll bring in LC here, and then this will be just T, and then it becomes rho C times LC square, simply because I'm multiplying and dividing by LC. And then what I will do is I will do one more thing. I will multiply this and divide this expression by K. Okay, K being the thermal conductivity. Okay, so if I do that, let's say I have this minus HLCK T by rho C K LC squared. Okay, and then what I will do is I'll do a simple simplification. I'll just write this as HLC by K multiplied by what? So this would be, I brought this HLC by K here, so this becomes K times T by rho C LC squared, maybe. Just correct me if I'm wrong, but this should be this. So because I've got this HLC by K here, this is basically here, so it remains KT rho C and LC square, which is basically this. Okay, all right. So now, can you tell me? Okay, I'll do one more simplification. I can write this as exponent of minus HLC by K into T by rho C by K LC square. Okay, that's simple. I just brought this K to the denominator. Okay, so now tell me what is this? We just now saw. What is this? So this is the bio number, right? That you just said just now. So this is the bio number. Okay, can you tell me what is this? Can you tell me what is this ratio? Density times the specific heat divided by the thermal conductivity. Yes, this is exactly equal to 1 by alpha, where alpha, so what is alpha? Can you tell me what is alpha? Alpha is known as the thermal diffusivity, right? So you have rightly pointed out this ratio is known as 1 by alpha, where your alpha is nothing but K by rho Cp, okay, and this alpha is known as thermal diffusivity. Okay, just like momentum diffusivity, where we studied that in fluid mechanics, it is analogous to the momentum diffusivity in heat transfer. We use thermal diffusivity. Okay, and just like the momentum diffusivity, which we generally denote it as nu, which is a unit of meter square per second, thermal diffusivity has also the same unit of meter square per second. Okay, and there is a this is just for your general knowledge. The ratio of this momentum diffusivity to the thermal diffusivity, this has also got a special so this has got a special name. And when you study convection heat transfer, okay, you will know this name. But do you know what is this called, the ratio of the momentum diffusivity to the thermal diffusivity? This is a very famous dimensional number. Yes, this is known as Prandtl number. It is named after the scientist Prandtl, and who it is the same scientist who who did all the analysis on boundary layer and all those things. So it is known as the Prandtl number. Known as My iPad is not working. Just 1 second. Right. Okay. Okay, I think it's working now. Okay. So this ratio, as I was saying, this is known as the Prandtl number, and we denote it as PR. And so it's we'll not study much on Prandtl number in this course because we don't have convection in this course. But the ratio of this the momentum diffusivity to the thermal diffusivity is known as Prandtl number. But anyway, if I now simplify this expression, okay, uh, if I now simplify this expression, it just becomes what? It just becomes theta by theta I, and then it can now be written as exponent of, okay, this can be written as the bio number because we have simplified this as the bio number. So it becomes minus bio number times, this is 1 by alpha. Remember, this is 1 by alpha. So this alpha would basically go there, and this can be written as bio number times alpha t, okay, by LC squared. Okay, now can you tell me what is this? This number has got a very special name. Can you tell me what is this? Yes, this is known as the Fourier number. Okay, and can you tell me, and okay, I'll just simplify this expression once more. So this is theta by theta I, and this is exponent of minus bio number times t by LC square by alpha, and this t by LC square by alpha is, as you said, this is known as the Fourier number, FO. This is denoted as FO. Okay, so your entire expression of your lumped capacitance model can also be written as now exponent of minus bio number times the Fourier number, FO, where your Fourier number is equal to t by LC square by alpha. Okay, so now can you tell me, is this Fourier number dimensional or non-dimensional? Is this Fourier number dimensional or non-dimensional? Can you tell me? Think about it. Yes, it is dimensionless. That is typically because your alpha has got a unit of meter square per second. Your LC square has got a unit of meter square. So your meter square and meter square gets cancelled out. And this time basically cancel out this time, okay, which is basically L square by T, the dimension of L square by T. Okay, this means that your Fourier number is dimensional. And always remember, when you have an exponential term, exponent of something, the exponent of that argument always has to be dimensional. Okay, you should remember that. So in the same analogy, your bio number is also a dimensional number because HLC by K is also dimensional. Typically because your K has a unit of watt per meter Kelvin, your H and LC has got a unit of watt per meter Kelvin as well, which means your bio number is also a dimensional number. But the importance of this Fourier number is that it speaks about a ratio of two time scales. Okay, we have one time scale T, which is basically the inherent time scale. This time scale is known as the inherent time scale. And we have one more time scale, which is basically this LC square by alpha. This time scale is known as the diffusion time scale. So in a way, the Fourier number is basically the ratio of, it speaks about the ratio of two time scale, the time scale of the problem, the associated time scale of the problem, which we call is the inherent time scale, divided by the time scale, okay, that the heat would require to diffuse into the body, basically. Okay. So this is basically the physical significance of the Fourier number, and you can also establish the expression of this lump capacitance model as a function of the Biot number and the Fourier number. But this is also one of your problems in your assignment, and in a way, like we have solved. So we have discussed this here as well. Okay. All right. Okay. So we'll stop here for some time. This ends the first agenda, like discussing on this lump capacitance series. In the next task, we will solve some problems associated with the lump capacitance model. But if you have any like questions associated with the discussion so far, feel free to like write in the chat box or speak up, or like or in any way you want. I'll just come in 1 minute. I'll just fill my mug and just come in a couple of minutes. Okay. Uh, let's see if we have any questions. Okay, so no questions. So, all right. Okay, so I think we are clear so far with all the like stuff that we did. I just repeat like for the sake of like having a quick recap. So what we did is we started off with understanding the lump capacitance model, okay, and basically this is the expression which governs how the temperature distribution inside this lump body would basically be a function of T. And we saw and we argued why this temperature is just a function of T and it's not a function of X, typically because we have a very low Biot number when we are using the lump capacitance model. Okay, and then this is the expression, the detailed derivation of this expression. I gave the hint. Just start off with the applying an energy balance here, and just basically use the fact that the heat that is going out is just the heat by convection, which is basically H times As into T minus T infinity. And because of this heat being going out from this body, there would be the rate of change of energy, or the rate of change of, you could say it's a rate of change of energy being taking place inside the body, which is basically nothing but rho times its volume multiplied by its heat capacity into this dt by dt. Okay, and if you just equate these two, you will end up getting an ODE. You can see this is an ODE, right? So you'll end up just getting an ODE, and this, if you just simply integrate this ODE, you will see that your temperature distribution basically follows this profile. Now it's important also to understand that in this temperature distribution, you can see that your temperature, either you see this or you see this, theta is basically, so remember this theta is nothing but this transform temperature that we are writing. So it's just another way of representing your temperature variable T. Okay. So it's important to like understand that your temperature is exponentially decaying with time in a lump capacitance model, which means at time t equal to infinity, your this t basically, so let's see what happens at time t equal to infinity. So when this t basically approaches infinity, this term will basically go to 0. which means if this goes to 0, you can simply find out that your T will basically be equal to T infinity. Physically, it means that your body, which was at some temperature, let's say Ti, when time goes to infinity, your body will be in an equilibrium with the neighboring fluid. And your temperature of the body will also be equal to the temperature of the neighboring fluid at time t equal to infinity. Which means your temperature profile, okay, your temperature profile essentially decays with time, okay, in a lump capacitance model. And this is also one of the problems in the assignment that I think you basically saw. Okay. All right. Uh, Okay, so let's now solve some problems related to this lump capacitance model. So this is a simple problem. It says that steel balls, okay, steel balls of diameter 12 mm are annealed by heating to 1150 Kelvin. So this term is a term in material science. This means when you are when an object is suddenly like subjected to, so there is a term called annealing and there is a term called quenching. So when an hot object is suddenly brought to a fluid or an environment in a colder temperature, then that process is known as quenching. And the annealing is the other way around. You are providing heat to the object from when it is initially at a colder temperature. Okay, so it says that steel balls of 12 mm diameter are annealed by heating to 11,100 Kelvin and then slowly cooling to 400 Kelvin in an air environment, and the ambient temperature of air is given to be equal to 325 Kelvin. Okay, the heat transfer coefficient is given to be 20. The properties of steel are given to your problem. This is a simple question. They are just asking to estimate the time required for the cooling process. Okay, so can you tell me in this problem what should be our first step? Like, can you tell me? So this problem appears simple, but yeah, to find LC. Yes, okay. So we'll find LC, and in this case, can you tell me what will be LC? LC is basically, so it's steel balls of diameter. So you can assume this to be equal to a sphere. So as you said, your LC will be just R by 3. Okay. Or in terms of the diameter, your radius is basically diameter by 2 by 3. So it becomes just D by 6. So your LC is basically 12 into 10 to the power minus 3 by 6 meters. Okay. All right. So once you know LC, what's the second step? Are we directly going to substitute it in the expression of this theta by theta equal to exponent of minus bio number times Fourier number, or like something else should be done? So we have not done an important step in this problem, and we saw that repeatedly that there is some criteria which needs to be satisfied before using the lump capacitance model. Can you think about what this criteria is? Yes, exactly. Bio number. So it's very important that when you get a problem like this, don't just blindly or naively just apply the lump capacitance model. Okay. You first need to ensure and check what is the bio number. So if you check the bio number here, the bio number is nothing but HLC by K. And your if you substitute the values, your H has got a value of 20 into your LC has got a value of how much? So it is, if you simplify this is 2, so it becomes 2 into 10 to the power minus 3 by the thermal conductivity, which is 40. Okay, so this LC has, so sorry, this bio number comes out to be around 10 to the power minus 3, which is basically equal to 0.001. So since your bio number is less than 0.1, so you can now apply the lump capacitance model. Okay, so always remember, no, don't just naively like apply the like lump capacitance models once you just see this question. Always try to ensure first the bio number and try to check that the bio number should be less than 0.1. If your bio number is greater than zero point 0.1 or let's say greater than 1, okay, you cannot, so your lump capacitance model, even if you apply, it will not be accurate and there will be a lot of errors in the calculations that you do. Okay, so since your bio number is less than 0.1, the lump capacitance model is valid Okay, and then you can just apply the governing equal. I mean, you can just apply directly the solution, which says that, okay, your theta by theta I, which is nothing but t minus t infinity by ti minus t infinity to be equal to exponent of minus. You can use any of the form. You can use exponent of minus t by tc, or you can use exponent of minus bio number times Fourier number, and anything you can use. So I generally like to use this bio number times Fourier number. Okay, and then you know all the values because you know what is t infinity. So t infinity is given to be equal to 325. Okay, and initially the temperature was 1150, that is also given, and it is, and the final temperature is also given to be equal to 400 Kelvin, which means what, this t is 400 minus t infinity is 325 divided by ti, which is the initial temperature, it was 1150, minus t infinity, which is 325, and then this is exponent of bio number is something we have already calculated. It is minus, oops, it is minus 10 to the power minus 3 multiplied by the Fourier number is nothing but it is alpha t by LC squared. Okay, and we just need to evaluate this time t. All right, so your first, so for that, first you need to calculate alpha. Alpha is nothing but k by rho c. Okay, and you know what is k by rho c, all those things are known. Your k is 40, rho is 7,800, and c is 600. Okay, so it is so how much is this? So this is 40 by the density. So your density is 7,800 times the specific heat. Specific heat is 600 joule per kg Kelvin. Make sure that the, like, all the units are in SI, and then you can calculate alpha. You can do this at your end. So what would be alpha? This just 1 0 goes, and this, I think this is 15. No, this is not 15. How much is this? So this 2 and this is 3. Yes, this is 15. Okay, so it is just basically 4 by 7800 into 15. You can do this calculation, and then you can just calculate alpha. Okay, from here you will get alpha, and you know what is LC, right? Length LC you have already calculated from this. So you know alpha. Okay, you know alpha, you know LC. The left hand side is completely known. You can just determine, just take the, just bring the exponent to the other side, and you can directly determine your time. Just do this calculation. I mean, this is just straightforward. You can just calculate, and your time would simply come out to be just around so I did this at my end. Your time would just come out to be around 1122 seconds, and if you convert this into hour, it will be around 0.312 hours. Okay, so this is the time. So this is the time that the steel ball should basically require. Okay, uh, which were initially at temperature 1050 to basically come down into 400 degrees Celsius in an ambient fluid having a temperature of 325. Okay, it's around, it's around 0.3 hours basically. All right, so I think this is clear. uh, I'll stop here for some time. If you have any questions, you can just ask me. So you can use any of this form. You can either use bio times Fourier in this equation. You can either use exponent of minus t by tc. Then you need to substitute what is the expression of tc. You can just use any of the forms that you like. Okay. So personally, I just like to use this form, and that's why I wrote this as bio times Fourier. So these are all the same as we have just seen it some time back. Okay. All right, we'll stop here for some time, and then we'll proceed with the next problem. The next problem is an important problem, and like we will see how basically it goes. Okay. Meanwhile, like if you have any doubts, you can ask me, or else you can read this problem at your end. Okay. So let's do this problem. This will be the last problem that we'll do, but it's an important problem. So it says that a chip of length 5 mm on a side and thickness 1 mm is encased in a ceramic substrate, and its exposed surface is convectively cooled by a dielectric liquid of some H and some T infinity. So what it said is that we have a chip, let's say a semiconductor chip, okay, it's inside a substrate, okay, and its exposed area, which is basically the shaded area, is it's exposed to a fluid having a temperature T infinity with a heat transfer coefficient H. Both of these things are known, okay. It says that in the off mode, the chip is in thermal equilibrium with the coolant. This substrate basically is the coolant, and sorry, this not this substrate. Sorry, the air which is passing over the fluid is the coolant. So typically in electronics industry, this is how it is done, right? So let's say in your laptops, you have the chips being embedded in the motherboard, let's say, and you have the fans. You have those big fans, okay, in your laptop, or let's say in any, let's say, workstations or in any big CPUs. You have those big fans which blows air in order to cool the chips, okay, or else your system would basically like slow down because of the heat unable to now dissipate, okay. So if so in order to remove the heat, what they do is so you have these fans in your laptops or in your like desktop computers. So these blows air in order to cool the chip which are embedded inside your inside the devices, okay. So this is what is also done here. So it says that in the off mode, the chip is in thermal equilibrium with the coolant. When your computer is off, of course, the temperature of the ambient is equal to the temperature of the chip. But when, let's say, the chip is energized, however, its temperature increases until a new steady state is established. So it's like when you turn on your computer and let's say you are playing a game, okay, your chip your chip temperature would now increase, okay, from an initial temperature which was in equilibrium with the room temperature to a new temperature, and after an initial transient it will attain a certain fixed temperature, of course, which is higher than the room temperature, okay. That's what it says. Until the chip is energized, however, its temperature increases until a new steady state is established. For the purpose of analysis, the energized chip is characterized by an uniform volumetric heat generation with this much. So it is obvious, right? Because let's say in your computer or in your motherboard, the means of the heat generation is basically coming place so it's a volumetric phenomenon, right? So this is also what they have said. The heat generation is a volumetric heat generation with magnitude this much, and this is taking place inside the chip, of course. Now, assuming an infinite contact resistance between the chip and the substrate, so they're saying that there is an infinite resistance here, meaning that so the meaning of infinite resistance is that since the resistance is infinite, you know that the rate of heat transfer is basically equal to some temperature divided by resistance, and if the resistance is infinite, your rate of heat transfer is basically zero. So now if the chip and the substrate have an infinite resistance, this means there cannot be heat transfer taking place from the chip to the substrate, okay. That is what it means, which means the only way the chip can dissipate heat is to the ambient air, which is basically flowing on top of it from the exposed area, of course, okay. That's what it says. Assuming an infinite contact resistance within the chip and the substrate and negligible conduction resistance within the chip, this means that as we have said that the bio number in this problem is less than 1. This is another way of saying that there is no conduction resistance in between this chip, which means that your temperature within the chip is not spatially varying. Okay, they're asking to determine the steady state temperature TF, that is the temperature after which, let's say you are playing a game and after which the chip would attain a steady state temperature. Okay, following activation of the chip, how long does it take to come within 1 degree of this temperature? Okay, then it says that after activation, so first of all, you need to find the steady state temperature, okay, after that initial transience period. In the second question, they are asking that they are saying now let's come to the transient period and let's see how long does it take to come within 1 degree of this temperature. Okay, that's the second part of this problem. And then they have said that the chip has a density of 2000 and a specific heat of 700 joule per kg Kelvin. So this is a little bit of a big question, but this is kind of a very important and a very practical question. I want you guys to read it first. So there are two objectives, okay? If you remember there are two objectives. So to find first the steady state temperature, which they call it as TF. This is basically the steady state temperature. It's the same temperature. Let's say you turn on your laptop After some time, so there is an initial transient where your temperature of the chip or your motherboard will basically rise. And after a certain transients, okay, let's say you are not running any more programs in your laptop, so it has reached a steady state. They're asking us to find that steady state temperature in the first question. So we'll not think about this initial transient period taking place in the first part. And then in the second part, what they're saying is that now let's come into the transient period. And then they have said is that following activation of the chip, that once you start your laptop, let's say, how long does it take, okay, to come within 1 degree of this temperature? Okay, this means that once you reach the steady state temperature TF, how long does it take to come within 1 degree of that particular temperature? So basically, they're asking us about the time in that initial transients. Okay, how much is that initial transients time? After that, which you reach this initial, the steady state temperature TF. Okay, so in the second state, they're just asking you about the time. All right. So this is what we need to find out. I want you to once again read the problem nicely, and then we will see how basically we need to proceed this sum. So is the problem statement clear or not? Like, did you understand the problem? Uh, or do I need to repeat it? Okay, yeah. Okay, thank you. Okay, so I hope you have understood it. So, okay, so let's start off with the first part. Okay, let's start off with the first part. So in the first part, remember what they're asking. They're asking us that after that initial transients, okay, after the initial transients, what is the steady state temperature? Which means in the first part, we don't need to think about the time factor being coming into the picture, because they have already said that after the initial, transient period, once your chip reaches a steady state temperature, we just basically need to evaluate the steady state temperature. So which means for the first part, I can simply write that if I just simply apply an energy balance in this chip, okay, let's say I consider this chip as my control volume, and I know that the only way this chip can dissipate heat is to the outside fluid. That is typically because the problem itself says that there is an infinite resistance between this chip and the substrate. So there won't be any heat transfer in this direction. Okay. So what I can write is that under steady state, so what? So under steady state, if I just apply energy balance in the control volume, and the control volume is basically nothing but the chip itself. So this is basically our control volume. Okay. So what I can write? So I can write that the energy which is generated, okay, inside the chip minus the energy which goes out from the chip at steady state. And since this we are doing at steady state, what will be the right hand side? Will it be a derivative of time or will it be zero? Can you tell me? What is EG? So can you tell me, will it be this or will it be this? Can you tell me, will it be option A or option B? Yeah, it will be zero. Exactly. So it will be just this. Okay. Since so try to understand. Although this is an initial, so this is an initial transience problem. In the first part, they are telling us do not worry about the initial transient state. We are just asking you that after that initial transient state take place. So it's just that once you just turn on your laptop and your chip temperature rises from a particular equilibrium temperature to a steady state temperature, we are just asking you that after the total initial transients, what is the final steady state temperature? Okay, and then we can do this analysis in steady state typically because we don't need to worry about that initial transients. Okay, so under steady state, if we apply the apply energy balance, okay, this is basically energy balance in the control volume, I can simply write out that the energy that is generated inside the chip minus the energy that is going out from the chip, this is equal to zero. Of course, the chip is at a higher temperature than the ambient, so there won't be any energy coming inside the system. So we have not written E dot in here. So basically, this becomes E dot G is equal to E dot out. So E dot G is known, right? Because we know what is the volumetric heat generation inside this chip. This is basically this. This is 9 into 10 to the power 6. It is nothing but Q dot. But since this is the volumetric heat generation, this so if you want to write this in terms of energy, Q dot is basically in watt per meter cube. So if you want to write this in terms of watt, I need to multiply with the volume of the chip. So this would be what? This would be the area which is L square times its width or the thickness. This thickness will write it as W, typically because we have used the small ts time. So the thickness we'll just write it as W. So we'll just write this. We won't use T here. We'll just write it as W. Okay. So this is Q dot into Q dot L square into W. And can you tell me what is E dot out? That's simple, right? How is the chip dissipating and its energy? So it's dissipating its energy to the ambient air by convection, right? Because we know that the chip and the substrate on which the chip is embedded has an infinite resistance, so that there is no way the chip can dissipate heat to the substrate. So what the chip will do is it has just one option. It will dissipate whatever the, yes, exactly, it is HA Ts minus T infinity. Yes, exactly. So what the chip will do is whatever the energy that is being generated inside the volume of the chip, it will just dissipate to its ambient air that is being flowing. Okay, so it is just H times the area. So the area would be just L square. That is typically because this is the area through which the chip is dissipating in energy. So this area is basically equal to L square. Okay, so it would be H L square times this is the final temperature TF. Now, can you tell me, is this temperature a function of time or not? Will TF be a function of time, or it will be just a constant value? Yes, can you tell me? Uh, so this is the critical part. Okay, can you tell me, is this a function? Think about it. Think about what the number, what we are doing here. Okay, under steady state, can this TF be a function of time? It can't be a function of time, right? That is typically because we have already stated that we have discarded the initial transient, that is the temperature from which the chip, which was initially at room temperature, it rises to some initial temperature, and after it reaches that initial temperature, okay, we are just looking at that period. Sorry, not the initial temperature, the final temperature. So it rises from an initial temperature to a final temperature in the initial transience period, and once this final temperature is reached, okay, it has attained steady state. Okay, and we are basically looking into that TF. So if I just denote, if I just denote this by a graph, if I just plot the chip temperature, let's say the chip temperature as a function of time, this would basically be something like this. So initially at time t equal to 0, it has some temperature Ti. So its temperature would basically rise. Okay, I am not saying it will linearly rise. I don't know what it will basically be, but I am saying that it will rise. But after a certain time, okay, after a certain time, it will eventually reach steady state as the problem has stated, and then this temperature would basically be constant. It is that TF that we are basically finding here. It is that TF that we are basically finding here. Okay, so this TF cannot be a function of time, right? Because it has reached this initial. Yes, exactly. Okay, so I hope you have understood this. So this TF is not a function of time. Okay, all right. So it is basically the steady state, and this portion is the unsteady state. Okay, this is your unsteady state. Okay, so this TF cannot be a function of time, and this TF is basically TF minus T infinity. I mean, this convection heat transfer is HL square times TF minus T infinity, and from here they are just asking us to find this TF. Okay, so this L square and L square would basically cancel, which means your TF is nothing but T infinity, okay, plus Q dot times W by H. Okay, I think it's just that. It's Q dot times W by H. And if you just substitute the values of this, so T infinity, I think T infinity is what? T infinity is 20 degrees Celsius. Q dot is known, right? The volumetric heat generation is known. It is 9 into 10 to the power 6. 9 into 10 to the power 6 into the width. W is given to be equal to, I think, what is W? W is 1 mm. So this becomes 10 to the power minus 3. And your heat transfer coefficient is what? Your heat transfer coefficient is 150. Okay, this is 150. And if you just simplify your TF, just do this calculation. If you just simplify, your TF would come out to be around 80 degrees Celsius. This means that from an initial temperature which was at 20 degrees Celsius, so this temperature is at let's say 20 degrees Celsius, your final temperature, this TF, is 80 degrees Celsius. Okay. And after this, it attains a temperature of 80 degrees Celsius after this, initial transience is felt. Okay. That's the first part of the question that we basically did. All right. Okay. So I hope this is clear. I'll wait here for a couple of minutes. If you have any doubts, you can ask me, or else we'll proceed with the second part. So just be clear that this is not a linear profile. Okay. In fact, I don't know, because there is heat generations inside this chip as well. You cannot directly say that it will be an exponential profile, and we'll just see why this is not an exponential profile, and we will see that why the direct formula of lump capacitance, that is theta by theta I equal to exponent of bio times Fourier. This cannot be directly applied here. Okay. We will see that shortly. So I don't know basically that will it be an exponential rise, typically because there is also heat generation taking place inside the chip. But at least I can say for sure that this can't be linear. Okay. So basically you can just think of it like a rise, but you cannot like critically determine what is the slope, or what basically the nature of this curve. Okay. For that to determine, you need to evaluate the temperature profile. Okay. All right. So let's go into the second part. In the second part, what they said is that once you turn on your, let's say, computer, which means your chip has now become activated, how long does it take to come within 1 degree of this temperature? This means to come within, let's say, 1 degrees of this 80 degrees of this final temperature. Okay. What's the time that you are basically going to take? So what they're asking is, let's say you want to reach, a certain temperature here. Okay, let's say this is some temperature, let's say alpha. This alpha is, you can assume this alpha to be around 1 degrees of 80 degrees Celsius. So so if you want to reach this alpha temperature, how much time basically you require in order to reach this particular temperature? So this means now we are inside this transient zone. So now we are inside this unsteady zone or transient zone, and for that we need to now basically solve for the unsteady problem inside the control volume. Okay, now my question is, can you directly apply this expression of theta by theta I equal to exponent of minus bio times Fourier? Because this also gives us the time, right? Your time is embedded in this Fourier number. And you know all the temperature. You know what is the final temperature. You know what is T infinity. You know what is Ti. This means technically you can use this expression to just calculate the time. But my question is, can you apply directly this expression? And if not, if yes, why? And if not, why you cannot apply this 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 direct form? I mean, why you cannot directly apply this formula? Can you tell me? I already gave a hint. In fact, I already said the answer. But yeah, formally, like, can you tell me why you cannot? So my question is, can you apply this? Sorry. Yes, can you give it a try? I mean, you can just give it a try, right? The worst case, it can be that the answer would be incorrect, but at least you have tried. Okay, I'll give you a hint. So when you derive this expression of theta, yes, t equal t in the denominator will be 0. Okay, okay, that is correct. Yeah, that is the one way of saying it, but I won't say that is exactly, that is not the physical answer. I won't say this. What you are saying is this is basically t, so this is ti minus t infinity, and you said that this ti was basically equal to t infinity, which renders now the fact that this denominator would basically become equal to 0. Okay, that is fine. Then, and maybe this is the reason. So mathematically, yes, this is the reason why you cannot apply the Fourier, sorry, the lump capacity, directly the formula of lump capacitance model. But this is not the physical answer. physically it's little bit, it's not that. Yes, you are correct mathematically, but physically it's not that. So remember, sorry, not remember, but what I want to say is, when you derive this expression, of the lump capacitance model, did you consider heat generation inside your object? Did you consider heat generation inside your object? uh, if you remember. So we didn't, right? Because, so when we derive this formula, what we did is, whatever the energy that is going out is basically equal to the rate at which your energy is changing. It is basically dE of the CV by dt. So one second. So when we, yes, exactly. So when we derive this formula, we did not consider that there is a heat generation taking place inside your object. Okay, because this E dot out is basically the energy that is going out from the object by convection, and this is just the rate of change of energy inside the control volume. Okay, but in this problem, they have stated that that's the very nature of the problem, which they have stated that there is a heat generation taking place inside this chip. Okay, so that's why there will be an additional heat generation term in the governing equation. Okay, which which will appear, and due to which you cannot directly apply the formula of your lump capacitance model. And that is why I always stress on the fact that do not just memorize formula, you should know how the formula basically came from the first principle. And the first principle here is basically nothing but the energy balance. Okay. So now, since you cannot directly apply this formula, okay, what we will do is we will start off from the first principle. So we'll just apply. So what we'll do is we'll just apply energy balance, but now we'll do it in the unsteady part. Okay. So we'll apply energy balance in the unsteady part in the control volume. And then what do we get? So this basically gives us the fact that your energy that is going out plus your energy that is generated is equal to the rate at which your energy is changing inside the control volume. Okay, so your energy that is going out is nothing but minus h times the temperature. This temperature will now be a function of time. Typically, because as I said from the graph, we are now in the unsteady zone, and this would be T minus T infinity. Okay, multiplied by L square, of course, plus the energy that is generated is nothing but the rate at which the volumetric heat generation rate multiplied by its volume, which basically becomes L square times W. And this, we have seen, this is nothing but rho times the volume times the heat capacity, okay, times this dt by dt. Okay, so this is precisely the governing equation which we now need to solve in order to find out the time. Okay, basically in order to find out the time such that there is a 1 degree difference between the attained steady state temperature. Okay, so if I basically solve this, sorry, I mean simplify this, it will be t, which is now a function of time, minus t infinity into L square plus q dot L square W equal to rho volume is, your volume is basically L square W C times dt by dt. So your L square gets cancelled. Okay. And what I do is I'll just take this term to this side so that it becomes rho times WC into dt by dt plus your h times t minus t infinity, which is equal to q dot times w. Okay, and what I will do is I'll just divide this equation by rho wc on both sides. So I'll just get dt by dt plus h by rho wc into t minus t infinity equal to q dot by rho c. W would basically get cancelled. Okay, and since this quantity is directly known, right? Your density is known. Okay, your density is known, your heat generation rate is known, and your specific heat is known. This is just a known quantity, and for the sake of simplicity, I'll just denote it as some alpha. Similarly, You know this quantity directly. You know what is the heat transfer coefficient. You know what is the density. You know what is this W, the width, I mean the thickness, and this heat capacity C. I will just call this as beta. Remember, this alpha and beta, these are directly known, and these are just some numbers. You just need to put the values and get the values of alpha and beta. But the equation, once we just simplify this, it just boils down to the equation like this. So it is dt by dt plus beta times t minus t infinity equal to alpha. And what I will do is I will just take this beta and t infinity to the other side because it's a known quantity, and this becomes dt by dt plus beta times t equal to alpha plus beta times t infinity. Okay, so this is the governing equations which governs how the temperature of the chip would rise once you turn on till you reach the steady state temperature. Okay, where this alpha and beta, these are just the properties, and you just know from the tabulated data. All right, so finally, how do we solve this equation? Remember, this t is the unknown that we are trying to solve first. I mean, this t is not the, so basically they're asking us the time, but anyway, we need to first solve this OD, right? Because your temperature now depends on time. The time that you put here will basically dictate what's the temperature that you get in the unsteady scenario. Okay, so how do we solve this? OD? Did you see in your maths class, at least when you were in your higher secondary or in your first year of your degree? Did you see this kind of equation? Can you just tell it with an yes or a no? Like, did you see these kind of equations? See, it's a linear equation, as you can see, because this is just a constant. Okay, alpha plus beta times t infinity is a constant. We know everything. Beta is also the constant. So this is a linear equation, which is non-homogeneous, of course, but it's a first order linear equation, right? So we know how to solve this, right? Do you remember something which is known as integrating factor and all those things? Have you learned this? Can you tell me? Okay, yes. All right, thank you. So the the methodology for solving these kind of like linear first order, non-homogeneous equation is by something which is known as the integrating factor. So what you need to do is you need to calculate the integrating factor. For instance, if you have an equation something like this, dy by dx plus some p which may be a function of x times y equal to some q which may or may not be a function of x. Luckily in our case, these p's and q's, okay, these are not of the function of time and these are just constant. So can you tell me in our case what is p and what is q? Can you tell me by comparing this canonical form to this form? Yes, quickly, can you tell me what is p at least? That's simple, right? Just compare this equation to this equation. Compare this equation to this equation. Yes. So your P is just beta, right? It's very simple. Your Y is just temperature, X is just time, and in that case, your P just happens to be equal to beta, and your Q is nothing but alpha plus beta times T infinity. Okay. So your P is just beta, and your Q is basically alpha plus beta times T infinity, where alpha and beta are basically this. Okay. So once you have this form of the equation, your integrating factor, as I was telling, your integrating factor is nothing but e power integration p dt, which means it is e power integration p is basically your beta times dt. Okay, and this is nothing but e power beta is just a constant, so it just becomes e power beta times t, and this is your integrating factor. Okay, so your integrating factor is nothing but e power beta times t, and if you just substitute the value of beta is nothing but h by rho wc, so it is just h by uh, rho wc. This is multiplied with just the time. So this is your integrating factor. So once you know the integrating factor, the solution is your t, which is a function of time, the temperature, which is a function of time, times the integrating factor, which is e power ht by rho WC, and this is equal to integration Q. Your Q is this term, alpha plus beta times T infinity, alpha plus beta times T infinity. This is your Q times the integrating factor, which is e power, HT rho C, and this is integrated with respect to time, plus the constant, which is the constant of integration. Okay. So that's it, right? You just need to solve this in order to get the particular temperature, and then if you know the temperature, you can just substitute the value of T in order to get the time. Okay. That is easy, right? Because this directly comes out of the integration because it's a constant. So it becomes T as a function of time equal to e power, HT rho WC, and this is equal to alpha plus beta times of T infinity. Okay. Integration of e power some constant time x, you know this is just that constant, so it will just be what, it will just be e power HT by rho WC divided by HT by rho WC, I hope this is correct, plus some constant. Okay. Now how do you evaluate the constant? That is easy, right? Because so that's it, that you have just evaluated the temperature profile here. Okay. And this constant can be evaluated just by using the fact that at time t equal to 0, you know that your t at time t equal to 0 is just some t initial, and this t initial is nothing but your t infinity. So from that you can evaluate this constant, and once your constant is known, you have the entire knowledge of this temperature profile. Just substitute the values here, you know all these alpha, beta, and t infinity and everything. All you need to do is, in order to get a 1 degrees closer to your TF, you just need to substitute this in this capital T, and you can calculate this small t, the temperature that basically you require. Okay. Right. For instance, uh, let's say I'll just show you. So I hope you can understand that, right? I mean, you got it right, how to evaluate. So for instance, this constant you can evaluate that at time t equal to 0. Uh, Follow. Did I make a mistake here? Okay, yes. This, there won't be a time here, right? So there won't be t here because it's just the constant part that will come out of this integration. Okay. So what I was telling that if you put time t equal to 0, so e power 0 is just 1. So if you just, so let's do it. So at t equal to 0, so what is your constant? So e power 0 is just 1, and your t is just t infinity. So this becomes t infinity, and this is alpha plus beta times t infinity, which you guys know already. And then this becomes what? This becomes 1 by h w h rho WC. Okay, because e power 0 is just 1, and this constant. So the value of this constant is nothing but, so the value of this constant is nothing but t infinity minus this bunch of term, which is alpha plus beta times t infinity times rho c will go up, and then this is divided by h. So that's all. That's your constant. So once you know this constant, you entirely know what is the temperature profile. Okay. So the idea is, now you know, if you know the temperature profile, it is said that to get into 1 degree closer to your final temperature, so you know that your TF came out to be equal to 80 degrees Celsius. That means your now T would be 80 minus 1, which is 79. So it's just that you need to substitute this value of 79 and try to find out what is this value of T in order to get to 79 degrees Celsius. It is all they are saying is that in the transient period, okay, how much time would you require to get to the 79 degrees Celsius mark, which is 1 degree closer to the final temperature. Are you clear? Like, how do we get the time? I mean, I'll not do this because it's like it will just involve some algebra. But in principle, are you clear? Like, what basically we need to do? So I have done up to evaluating the constant. Just substitute all these value, you'll get the numerical value of the constant. And thereafter, just substitute this T to be equal to 79 degrees Celsius, and you will just get this time. So I'll just tell the answer. Check it out at your N and C. If you put this T to be equal to 79 degrees Celsius, you will get the time to be around 38.3 seconds. Okay. So is it clear? Like, how do you basically end up getting the time? Can you just, or do I need to repeat? Okay, yes, okay, thank you. So anyways, you can do this at your homes. It's just the numerical, okay? It's just the numerical. So you just evaluate this constant. You know all these values, just evaluate this constant. Okay, then you will get the temperature profile. Once you get the temperature profile, just substitute this as 79 degrees Celsius and just calculate this time. That's all. Okay. Okay, all right, guys. So if it is clear, that's well and good. So this is little bit of an important and an involved problem where we saw that just blindly don't follow the don't follow formulas, because we saw that since there was heat generation, taking place inside heat generation taking place inside your slab, you cannot directly apply your lump capacitance formula, that is theta by theta I as exponent of minus T by Tc. And yeah, so basically what we need to do is we need to start off from the first principle, since there is now heat generation, and then we encountered an ODE, a linear ODE, which we solved and basically calculated what the temperature profile would look like, and the uh, final answer, which asks that in order to come to 1 degree close to the final temperature, that is, they are just basically asking how much time will it now require to reach 79 degrees Celsius. That's what they're asking. And this time should roughly come out to be around 38.3 seconds. Just do this math. I just need to plug in the values and do this math, and you should get this time to be around. Okay. So with this, we will stop the discussion. We'll stop today's discussion. If you have any questions, you can ask. I'll just wait for a couple of minutes. Or else, like, if you have questions later on, you are feel free to like post it in the discussion forum, and I'll be happy to address them. Okay. So if no questions, then we'll call it a day here. Thank you very much for joining, and we'll meet on the next on the next Saturday as usual. The usual timing on Saturdays from 3 to 5 that you guys all know. Uh, so we'll meet on next Saturday from 3 to 5 p.m. That's the usual timing, and we'll learn something. So we'll learn something which is known as a semi-infinite object, and then we'll proceed to the like discussions on the next week and the associated problems we did. Okay. All right. So thank you very much, guys, for attending. I'll stop. I'll stop the meeting today, and if you still have any further questions, you can just post it in the discussion forum of the group. Thank you very much. See you guys on the next Saturday. Thank you.